In this video, I'm going to start talking about conditional probabilities, which is where most people really start having trouble with this probability stuff. It can be quite unintuitive. And so a conditional probability is one uh, that says the probability of A given B, where that vertical line means given. So it's the probability of some event A will occur given that event B has occurred. And so mathematically it's defined like this. And we'll get into talking about, what that means here in a little bit. But I wanted to show sort of pictorially what we've gone through so far. So in the upper left here, we have the probability of A. And so inside the box is sort of, the exhaustive probability of whatever you're talking about, or uh, what's in A is the probability of A, and then everything outside of that green circle is the complement of A, both of which will have to add up to equal to 1. And so everything in the box is sort of, everything that we are talking about. And then so we have the probability of A or B, which, we have the everything in A and then everything in B, and then we have everything that has A and B, so in the middle. And remember, we don't want to count that twice, so we end up subtracting one of those out. But we see that this is the inclusive OR. So it's A, B, and then A and B, sort of all added up together. Then, of course, we have the probability of A and B, which is just this part here in the middle, this sort of wedge here in the middle. So is that part sort of as a proportion of to everything inside the box. So it's everything inside the box. So essentially what's in this dark gray here is the numerator, and then everything in the entire box is the denominator in our proportion. So then when we get to the probability of A given B, we end up, well, sort of everything in the box is sort of whited out or bleached out, except in B, and then in this part where B and A overlap. And so what we're saying, so when we say given B, we're saying that the the red circle, everything in the red circle, so something in the red circle has definitely occurred. And so we rule out everything outside of the red circle. And then we say, what is the proportion of A in B here? So the proportion of this gray, this dark gray wedge to the entirety of B here. And we'll see why that is important to understand that we are sort of collapsing everything down to just within the B here, because that gets into base rates, which is going to be the topic of the next video. And that's a place where people often go wrong when thinking about conditional probabilities. And so to look at that, so a conditional probability is essentially the probability of the then in an if-then statement. So if we consider the probability of getting struck by lightning, so the probability you will be struck by lightning, and then we could put other things in if, but here say the if is you are out in a storm, and so what is the probability that you are struck by lightning given that you are out in a storm? And so then we want to find the probability that is true that you will be struck by lightning given you are out in a storm. And so this you can see is different than just the probability, and I'll just use S here. So the probability of getting struck by lightning would be, I guess we could say the probability of getting struck by lightning down here is everything in A here, which we can see is sort of a small amount of the box of all people. And if this was realistic, it'd probably be much, much smaller than that. But we can imagine that this green circle of people who are struck by lightning is going to be much smaller than the box of all people. I mean, it's almost proverbial that getting struck by lightning is a rare event. We always say things like you have a better chance of getting struck by lightning than winning the lottery or things like that. So we know that A is small. But then if we focus down, if we sort of focus down on B here, which is all the people who are walking in a storm. And then we take the probability of people who are struck by lightning while also walking in a storm. So the proportion of this dark gray wedge here to the light gray B is going to be much larger than the proportion of A to the denominator of all people. And so the probability of A given B is the proportion of P, A, and B in just B here. And so we see how having the given here is sort of collapsing down, is sort of getting rid of a bunch of people from our denominator. It's really reducing our denominator in the proportion here. So we have another example here. So the Grays have two children, the oldest being a girl. What is the probability that both children are girls? So this is the probability of first is girl and second is girl, given that first is a girl. So we have the probability first is a girl and second is a girl, which is 0.25, because we know you can have girl girl, which is 1. You can have girl boy, which is 2. You can have boy girl, which is 3. You can have boy boy, which is 4. And then the probability of girl girl out of all those things is 1 in 4. And then so we have the probability that the second is a girl, because we already know that the first one is a girl. So we just want the probability that the second one is a girl. Well, the second one could be a boy or it could be a girl. And so it's 0.5. And so 0.25 divided by 0.5 is 0.5, because the 0.25 is half of 0.5, so it's simplified to 1 over 2. And so we can look at the classical definition over here, which, so like I said, we know the first one is going to be a girl. So we have collapsed down our sort of possibilities. So, the original possibility is that the first child could also be a boy, but we'd sort of ejected those possibilities and said we know that the first one is a girl. And so we're just looking at the probability of the second one. So we see that just this top one that I have highlighted in red here is the probability of that both are a girl, given the first is a girl. And so we can see that that is 1 out of 2, or half. And so now we can talk about the mathematical definition of independence. So I said in the video on conjunction that I'd give a more mathematical definition of independence. And so we can say that A and B are independent if the probability of A is equal to the probability of A given B, and that the probability of B is equal to the probability of B given A. And so we see that, what this is saying is that the probability of A is not affected by B being a given, and the probability of B is not affected by A being a given. So even after we know that B has happened, we can't change our probability of A. So sort of in the example up here, if we are saying that the probability that the second child is a girl, which is our A, given that the first child is a girl, which is B, well, we wouldn't be able to change A. It would just be the same as the probability of A. It would still be 0.5%, and so that's why we say that they are independent. And so the probability of a conjunction P, A, and B when A and B are not independent is this. So I said in the conjunction video that the probability of A and B when independent was just of the probability of A times the probability of B. But now that we're not independent, we have this conditional here. So it's the probability of A given B times the probability of B, which you can see after we divide both sides by the probability of B, we just get back to our definition here of a conditional, which was what I had up here. And so that is if it is not independent. All right, so additionally, when we say A and B are independent, like I said, that means P, A, and B is equal to the probability of A times the probability of B. So in the example we used before with the 20-sided die roll, the probability of getting a 20 on the first roll and a 20 on the second roll is 1 over 20 times 1 over 20, which was equal to 1 over 400. But I said that only works when each roll is independent. We thus see that when both trials are independent, we have our probability of A given B is equal to this, which was sort of our definition of the conditional. But then we said up here that this P, A, and B is just equal to P, the probability of A times the probability of B, so we can make that change if these are independent. And now we just cross these off and we just get probability of A. So our probability of A given B is equal to our probability of A just by itself. So that is sort of the mathematical definition of independence. And so this is an example that Steven Pinker gives about sort of the unintuitiveness of these conditionals. And so this comes from what's called the boy or girl paradox, which you can look it up on Wikipedia or something if you want to get more, because I'm not going to go that far into it, because Steven Pinker, I don't know if he meant to do it sort of deceptively, gives a specific interpretation that makes it so that it's not really the boy or girl paradox anymore. But anyway, I don't want to get into that. So Steven Pinker says, so consider a family. The Whites have 2 children. At least one of them is a girl. What is the probability that both are girls? And so this is the probability that the first is a girl and the probability that the second is a girl, given that the first one is a girl or the second is the girl. And so we can simplify that to this. And so Steven Pinker says that many people think that it's half because they only consider the case where the eldest child is a girl and neglect the case where the youngest child is a girl and the eldest is a boy. So they sort of don't consider this or. They just sort of think essentially what we had up here. They essentially just mistake this up here, where just the first child is a girl. But if we go into the real answer here, so Steven Pinker doesn't go through this much detail, but I kind of wanted to go through the math here, so hopefully people will understand this a little better. So we know that the disjunction in the given is this. So that's just our definition of the disjunction. So the probability that the first one is a girl or the second one is a girl is the probability that the first one is a girl plus the probability that the second one is a girl minus the conjunction of the probabilities, which gives us this table. So we can have, this, or we can have this, or we can have this. And we see that this is sort of in, G1 and G2, or G1 and B2, or B1 and G2. And so we can say that that our definition of the disjunction here is just equal to P of, or probability of G1 and G2 plus the probability of G1 and B2 plus the probability of B1 and G2. But since there is a 0.25 probability for each of these conjunctions, because remember there is also the probability of boy 1 and boy 2, but since we are doing the given, we have collapsed that down, but we still have to use the probabilities given from the sort of full set of possibilities. So we know that each of these is just equal to each other and equal to 0.25. And so we therefore have the probability of the first one being a girl and the second one being a girl, given that one is a girl or two is a girl, is equal to this, where I just put this right here down in the denominator, and then our probability of girl, the first one being a girl and second one being a girl, in the numerator. And so that gives us this right here, which is 0.25 over 0.25 plus 0.25 plus 0.25. And then if we factor those 0.25s out, we get this. So it's just 1 over 1 plus 1 plus 1. This cancels, and so we have 1 over 3, and it's 0.333. And so that is, so that's the real answer here, given that Steven Pinker has sort of told us which interpretation of this problem he is going by. And if we look at the classical interpretation, we see that, we have this here, which is 1 out of these 3. So we've sort of gotten rid of this one. So it's just 1 out of 3 that you have 2 girls, given that one of them is already a girl. So I said there was another interpretation. I thought about going through it here. I'm not going to go through this here. But it is essentially these two ways of posing the questions. And so I got this here from Wikipedia. So Steven Pinker has already worded it such that he is using this interpretation. From all families with 2 children, at least one of whom is a boy. And so Wikipedia is using boy, where Steven Pinker and I have been using girl. But it's the same thing, just swap boy and girl. A family is chosen at random. This would be the answer of 1/3. So from all families with 2 children, 1 child is selected at random, and the sex of the child is specified to be a boy. This would yield an answer of 1/2. And so, like I said, Steven Pinker has already sort of worded it such that we are taking that first interpretation. But he is saying that the reason that people will mistake this is because they will take that wrong interpretation, or that wrong way of doing the math, essentially, of basically only saying that the first child is a girl and not considering the case where the second child would be a girl. And so, like I said, after we go through all this, we end up with the real answer, which is the 1/3 here. But anyway, I don't want to belabor this too much. So you may have noticed, like I said in here, I sort of purposely made this green one smaller, and in the next video is sort of where I'll be going into that in more detail, which is called the base rate. And the base rate fallacy or base rate neglect is a common thing that people do, which leads to sort of irrational answers to things. But anyway, I hope you found this video useful, and I will see you in the next one.